Welcome back to another episode of Second Career Pilot. Today, we're zeroing in on some absolutely fundamental aerodynamic factors that every pilot needs to have cold, especially when you're relying solely on the instruments. We'll be pulling our insights directly from CH4 aerodynamic factors to make sure we're all operating from the same baseline understanding. Think of this as your focused review of the core principles governing how your aircraft behaves, particularly when those visual references disappear. We're going to cut through the technical language and pinpoint what truly matters for safe and precise instrument flying. Okay, let's unpack this by starting at the very beginning. The airfoil. We're talking about the shape of the wing, right? Some key terms to nail down are the leading edge, that's the front, and the trailing edge, the back. Then you've got the upper and lower camber, those curves, and the mean camber line that runs halfway between them. And then there's the chord line, that straight line connecting the leading and trailing edges. Its length is just the chord. So with all those different curves, what's the real aerodynamic significance of that mean camber line for us pilots?
Well, the mean camber line, it's really key. It's not just some midpoint on a diagram. It basically defines the airfoil's aerodynamic personality, its shape, how much it curves away from the chord line. That directly influences lift, stall characteristics, everything. So when you're making tiny pitch changes on an instrument approach, remember, it's that camber line's shape dictating how well your wing's working at those critical slow speeds.
Right, and building on that, relative wind and angle of attack, AOA. Relative wind is just the airflow hitting the airfoil.
Hmm.
Simple enough. And AOA, what? That's the angle between that relative wind, or your flight path, really,
Yeah.
and the chord line. Super important concept. Flight path being the actual path through the air. So airspeed tells you how fast, but AOA tells you how much bite the wing has, yeah.
Why is that so critical in IMC?
Exactly, because AOA is what directly controls lift. Small changes there mean big changes in lift. When you can't see the horizon, you can't feel the airflow changes as easily. So understanding pitch, power, and AOA through your instruments is how you stay flying, how you avoid stall. It's fundamental. Okay, let's get into the big four forces then. Lift, weight, thrust, and drag. Classic stuff. Lift. We know it's perpendicular to the relative wind, acting up from the center of pressure, or center of lift. Its strength depends on speed, air density, wing shape and size, and crucially, that AOA. Straight and level, lift equals weight, but upwards is relative to the wing, isn't it? Not always straight up from the ground.
That's a really important point. Lift acts perpendicular to the wing. So in a bank, it's tilted. And yeah, the center of lift isn't always where the center of gravity is. CG is where weight acts down. In a descent, for instance, weight's actually greater than lift.
Good point. Then thrust, that's the engine pushing or pulling us forward, fighting drag, usually parallel to the fuselage. And drag, the force acting parallel to the relative wind, backwards. It's broken down into induced and parasite drag. How do these mess with us on instruments?
Drag. They behave so differently. Induced drag comes from making lift, so it's highest when you're slow and pitched up. High AOA, like takeoff or maybe holding slow. It actually goes down as you speed up because you need less AOA for the same lift.
Right, counterintuitive maybe.
Yeah, so if you're holding, maybe trying to save fuel at a lower speed,
Yeah.
you've got more induced drag.
Mm-hmm.
Need more power just to stay level, even if it feels stable.
Hmm.
Parasite drag, though, that's everything else. Skin friction, the shape of the plane pushing air, that skyrockets with speed. You feel that on approach if you're fast. It takes more power just to maintain the glide path because of that extra parasite drag.
And parasite drag itself breaks down, right? Skin friction, that air rubbing on the surface, boundary layer stuff, interference drag where airstreams collide, like wing roots, and form drag, just the basic shape resisting the air. Fairings help with that.
Exactly. And knowing this helps you anticipate. Like flaps down on final, you've just added a bunch of both induced and parasite drag.
Yeah.
Got to manage power carefully then.
Yeah. So the bottom line is, lift must beat weight. Thrust must beat drag. Understanding that balance is key to reading your instruments correctly when you're flying blind. Okay, let's quickly touch on Newton's laws. They're the physics behind all this motion. First law, inertia. Things stay as they are unless a force acts. In flight, gravity and drag are always acting. Our controls manage those forces. How does inertia feel on instruments?
Well, inertia means things don't happen instantly. You make an input, the plane takes a moment to respond, resists change. That's why smooth inputs are crucial in IMC. Jerk the controls, and you can easily get disoriented trying to follow the instruments.
Makes sense. Second law, momentum. Force equals mass times acceleration, basically. FMA. This covers how we change speed and direction using pitch and thrust. Speeding up, climbing, turning, all acceleration.
And think about controlling climb rate. Pitch plus power equals vertical speed change. That's the second law in action, interpreted through your VSI. Direct cause and effect.
And the third law, action-reaction. Every action has an equal and opposite reaction. Jet thrust pushes air back, plane goes forward. Propeller pulls air back, same deal. And lift itself. The wing pushes air down, the reaction is the upward lift force.
Yeah, it's not magic. The wing is actively changing the air's momentum. The third law explains that interaction. Very neat.
Let's talk atmosphere, mostly nitrogen, oxygen, but the key bit for us is that air has weight, 14.7 psi at sea level, and half the atmosphere's mass is below 18,000 feet. Why is knowing about air density so important beyond just performance?
Density is everything. It affects lift, drag, engine power, performance across the board. And remember, density changes with temperature and pressure. Hotter air, less dense. Higher pressure, more dense. Colder, denser. This doesn't just hit performance. It can affect your altimeter readings if pressure or temp are way off standard. Need those corrections.
Which brings us neatly to standard atmosphere, ISA. That baseline, 29.92 inches, 15 degrees Celsius at sea level, standard lapse rates. But reality is rarely standard, so we need corrections.
Absolutely. First step is pressure altitude. Set 29.92 on the altimeter. That's your height above the standard pressure level. But the real performance measure is density altitude. That's pressure altitude corrected for non-standard temperature.
Right, DA tells you how the air feels to the wing and engine. High density altitude, hot, high, or humid air means poor performance, longer takeoff, worse climb. You can use charts or a flight computer or that rule of thumb. Add about 120 feet to pressure altitude for every degree Celsius above standard. Understanding DA isn't just about takeoff distance, is it? It affects approaches, too.
Definitely. High DA means your true airspeed is higher than indicated for the same approach speed. So you're covering ground faster, need to plan your descent and timing differently. Crucial on a tight instrument procedure.
Okay, back to lift control. Always perpendicular to relative wind, not always up. Depends on density, wing area, speed, wing type, and AOA. Increase AOA, get more lift up to the stall point. We control it mainly with pitch for AOA and power for speed.
And that leads to the pitch-power relationship. To keep lift constant, if you slow down, you have to pitch up to increase AOA. Speed up, you generally need to pitch down slightly to maintain altitude. You learn this dance intimately on instruments.
Yeah, and using the elevator, especially pitching up, often means pushing the tail down, which costs energy, and aft CG can actually help reduce that a bit. Precise instrument flying really comes down to coordinating pitch for the flight path and power for the airspeed, like add thrust to level off and accelerate. You'll need to lower the nose slightly to counteract the extra lift from speed increase, right?
Exactly. It's a constant balancing act, reading the instruments and making those small, coordinated pitch and power adjustments. Continuous feedback loop.
Now, drag curves and the regions of command. Looking at power required versus airspeed, it's not a straight line, is it?
Not at all, because different drags dominate at different speeds. And propeller efficiency changes too, so engine power doesn't translate linearly to thrust available.
This gives us those two regions. Normal command, add a power, go faster. This is higher speeds, where parasite drag rules. Most flying happens here.
Right. Cruise, climb, maneuvers. Usually normal command.
But then there's the region of reversed command. This is the tricky one.
Here, you actually need more power to fly slower. This is low speed, high AOA, where induced drag is the big player. One power setting might give you two different airspeeds on this curve.
And that's critical on approach, right, if you get slow?
Yeah, if you get slow on final, deep in the reverse command region, just lowering a nose might not fix it. You might need more power to arrest the descent and regain speed. Very counterintuitive if you're not expecting it. Close to the ground in IMC, that's dangerous.
So most GA planes might only touch reverse command near stall, below approach speeds. But it's there.
And speed stability is different too. Normal command, the plane kind of wants to return to trim speed after a bump. Speed up, you have a power deficit. Slow down, excess power helps push you back. Trim helps a lot here.
But near the bottom of that curve, it's flatter, neutral stability. Speed changes, it just stays there. Requires more actor piloting.
Exactly. And in reverse command, it's unstable. Speed up, you get more excess power, speeds up more. Slow down, bigger power deficit, slows down more. Induced drag really drives this.
Makes precise speed control vital back there. Small errors can snowball if you're not paying attention, especially on instruments. Let's talk trim. Using trim tabs or adjustable stabilizers to take the pressure off the controls. Tabs deflect opposite the control surface, use airflow to hold it. But trim is speed dependent, right?
Absolutely. Change speed, you have to retrim. It's fundamental. For instrument pilots, good trimming is maybe even more critical, reduces workload massively, lets you focus on scanning, navigating, communicating. A well-trimmed plane almost flies itself.
Okay, slow speed flight, near stall or in reverse command. Final approach, go around, slow flight practice. Need lift equal to weight for level flight. Less lift, you descend. Often approach is flown around 1.3 VSO, which puts you near that neutral stability zone. What does that mean practically on an ILS?
It means you need precise, coordinated pitch and power. Small deviations won't really self-correct strongly. You have to be proactive. And configuration changes, like dropping flaps low down, you got to be ready for pitch changes you didn't ask for.
And to get more lift at low speeds, we use high lift devices. Flaps, vortex generators, flaps increase camber, plane flaps, split flaps, common types. They give more max lift, but interestingly, they lower the stalling AOA.
Yeah, the wing stalls at a slightly lower angle with flaps down, even though it makes more lift overall before stalling. Something to keep in mind.
And vortex generators, those little fins.
They delay boundary layer separation, create tiny swirls that energize the air close to the wing, helping it stick longer at higher AOAs. Both let us fly slower safely, which is great for approach and landing, but that lower stall AOA with flaps needs respect, especially in gusty IMC.
So instrument approach speeds. Smaller planes might fly faster, say 1.8 VSO, keeping them in normal command. Good stability. Small pitch tweaks work without power changes.
But bigger planes often fly closer to 1.3 VSO on final, puts them near neutral stability. Precise speed control is absolutely key. Might need temporary power nudges for small speed corrections. And the big danger for any plane: slow down too much, get into reverse command, sync rate increases, speed keeps dropping unless you add power and manage pitch correctly. Very easy to get behind the aircraft there.
Okay, turns. Need that sideward force. Banking creates it by tilting the lift vector. Part of lift still opposes weight, vertical component. The rest pulls you into the turn, horizontal component, centripetal force. Inertia gives the outward centrifugal feel. What's the big risk with bank angle and lift in IMC?
Load factor. Steeper bank means higher load factor. Stall speed increases with the square root of load factor. So if you're slow, maybe maneuvering in a hold, and you accidentally steepen the bank too much, you could stall at a much higher airspeed than you'd expect. Without visual references, it's easy to overbank.
Right, and that relates to rate and radius of turn. Rate depends on bank and speed. Faster speed, slower rate at constant bank. Steeper bank, faster rate at constant speed. Radius also depends on speed and bank. Faster speed or shallower bank, wider turn. Slower speed or steeper bank, tighter turn. Affects intercept angles.
And a standard rate turn, 3 degrees per second, is our benchmark. That rule of thumb for bank angle is your speed 10, plus 7. So 90 knots needs about 16 degrees bank. Useful estimate.
Now, coordination. Adverse yaw. You roll right, left aileron goes down, makes more lift, more induced drag, left wing slows, nose yaws left initially, opposite the turn.
Exactly. That's why we need rudder, especially when rolling into or out of turns on instruments. Keep that ball centered, smooths things out.
Slipping turn, too little rudder, ball inside. Skidding turn, too much rudder, ball outside. Got to coordinate.
And remember, in a turn, you need slightly more AOA, back pressure, to maintain altitude because lift is tilted. More AOA means more induced drag, so you might need a touch more power to hold speed.
Okay, load factor again. Ratio of aerodynamic force to weight. Load factor of 3 means 3 Gs. Planes have limit load factors based on category: normal, utility, acro.
And turns increase load factor. Steeper bank, higher Gs. Exceeding the limit load factor or the critical AOA leads to a stall. High load factor situations. Steep turns, especially slow. Structural ice adds weight and degrades aerodynamics. Turbulence. All things to be wary of in IMC. An unexpected steep turn can really load up the wings fast.
Which brings us to icing, a massive hazard for instrument pilots. Understanding conditions, types, effects, systems. Critical. Avoidance is key. Pre-flight planning, clean aircraft. Essential.
2 main types. Structural ice on the outside, induction ice affecting the engine. Structural forms from supercooled droplets freezing on impact. Thin edges ice fast as probes. Tailplane often show it first.
Induction icing. Blocks engine air. Carb ice is common in piston engines, even above freezing temps, sometimes due to Venturi cooling. Carg heat is the fix.
Fuel injected less prone, but intake blockage can happen. Jets can get inlet icing, engine probe icing, run back icing. Ingested ice is bad news.
And structural ice comes in different flavors. Clear, rime, mixed.
Clear ice, glaze. Dense, hard, transparent. Forms near freezing, high water content. Can make nasty horn shapes. Rime ice. Milky, rough, brittle. Forms colder, less water, smaller droplets. Can build out forward. Mixed is just that, a mix. Shape and roughness are the real aerodynamic killers.
And the effects on the wing, huge problem. Reduces max lift, reduces stall AOA. Might not affect cruise lift much, but dramatically cuts lift capability at higher AOA for landing. Stall happens earlier, faster. Even thin, rough ice hurts.
Drag goes way up too. Control surfaces can get restricted or blocked. The sheer weight can be an issue. Rule is ANI, ice, or frost removed before flight, non-negotiable.
And then there's roll upset in severe icing. Uncommanded roll due to flow separation can happen without stall warnings. Severe icing is outside certification anyway.
And tailplane stall. Flaps down or speed increase can put the tail at a higher negative AOA. Tail ices faster, often unseen, can stall the tail.
Symptoms: elevator pulsing, weird nose down trim, mushy elevator, sudden nose drop.
Recovery. Flaps up immediately. Nose up elevator. Increase speed. Power appropriately, maybe cautiously. Slow pitch changes. Dites if you have it. Critical point. Increasing speed might worsen a tailplane stall at the same flap setting.
Prop icing reduces thrust. Pitot-static icing screws up instruments. Stall warning can fail or be inaccurate due to ice changing the stall AOA. Windshield icing blocks view. Antenna icing causes vibration, signal loss.
Yeah, the list of problems is long. Lots of accidents linked to ice, especially takeoff ice. Avoidance is paramount for non-Fikey planes. Even Fikey pilots need vigilance, know their systems, and avoid conditions beyond certification, like SLD's supercooled large drops.
Okay, that wraps up our look into some key aerodynamic factors. Hopefully this has provided a clear understanding of these principles and their importance in your flying, especially when the visual cues disappear. Keep these concepts in mind as you prepare for your flights, and always prioritize safety through knowledge and diligent pre-flight planning. Thanks for listening.